way it goes is we have a field. The field is given by having 2x, ax. In other words, the x component is 2x and the y component is minus 2y, 4y. And then the statement of the problem says that we have a particle, charged particle, of 2 coulombs, and then it moves from the point 200 to point 000. In other words, it moves from this point over here to this point over there, and then in subsequent motion, it moves from this point over here to this point over there. And the question is, how much work is done when the particle moves from this? Now, the next part of the question is, now the same particle moves from this point over here to this point over there, but this time it moves along this line, the straight line over there. And again, the same exact question, how much is the work that will be done by this moving particle? The next question is this particle conservative? Right, okay, let's see how we can actually solve this problem, right? So, the work, the infinitesimal work, it's given by dW equals to minus the amount of charge we have, which is 2 coulombs, and then 2x in the direction of x, right? And this has to be multiplied by dx ax. Now, this is a relatively simple manipulation, so we're going to have the ax and the ax obviously in the same direction. So those unit vectors, when they multiply together with the dot product, the value is 1. So the net result is minus 2x, minus 4x, and then dx. Now, this is again what's happening if we go from this point to this point. Now, in order to find the entire work done, we need to integrate to see how much work ultimately is done by moving this charged particle of 2 coulombs from, let's say, point A to point B. The next movement is from point B to point C, and this is along the line from the point 000 to the point 020. Again, there's another infinitesimal walk, and this time is going to be equal to minus 2 again. This is the amount of charge we have, and then this, 4y dy, and I should not skip steps, so it's basically 4y in the direction ay, and then this is multiplied by dy, again in the direction of ay, the unit vector in the y direction. Same thing applies as before. In other words, the dot product of the unit vectors is equal to 1, so this gives us, this is minus 4y, so basically it's, y is doing that, 8y dy. Now, if I want to find the work done, the total work done by the movement of this particle, initially from the point A to point B and then from the point B to the point C, I need to take the integral. So I'm integrating. The total W is going to be equal to the, I think I'm doing something wrong and it keeps moving to the next page. So W is going to be equal to minus 4x, and that's the integral from the point 2 to the point 0 dx plus 8y again from the point 0 to the point 2 dy, which is 4x squared over 2, 0 from 2 to 0, plus 8y squared over 2 from 0 to 2. So if we substitute the values over here, there's a minus over there that I forgot to put. So basically this is going to be 4, 2 squared over 2. So it's basically 8. And then from the other one, we have 8y squared over 2 from, again, 0 to 2. So it's 8, 2 squared over 2. So 4 times 4, 16. So if you combine the summation of those two contributions of work that's been done by moving the particle from the point A to point B initially, and then from the point B to point C, the whole work is equal to 16 joules, or joules, whatever you want to call it. Now, the next question is, if we have the same exact thing, so we have, there is a point over here, 2, 0, 0, the 0, 0, 0 in, let's say, the center of the coordinate system, and then this is the 0, 2, 0. The question is how much work will be done if the particle moves along this line over there. First thing we need to do is how to define this line. We can say that y equals alpha x plus beta. And the way you find this alpha and beta, in other words, the slope of the line and the point that actually intercepts, we have to substitute values. If we put x equals 0, we know that y equals to 2. So if I plug over here x equals 2, y equals 2, that will be able somehow to find what is b. So basically 2 equals alpha times 0 plus beta. So from here we find that beta equals to 2. Please do not hesitate. If something's unclear, do not hesitate. So ask the question so you can. Now, so we found beta, now we need to find A or alpha. The way we do that again is that if we plug x equals to 2, then y equals 0. In other words, this point over here. So 0 is going to be equal alpha times 2 plus beta, that we found that beta is going to be equal to 2. So from here, with very simple mathematical manipulations, we can find that alpha equals minus 1. So our line is y equals minus x plus 2. That's the way we describe this line over here. Now, in order to find the work done for the particle to move from the point alpha or A to point C along this line, again, dW is going to be equal to x AX minus 4y AY was the description of our electric field. And if we make this sort of substitution, most of the times, the easier way somehow to deal with those things is that to express it parametrically with respect to a third variable, but in this particular case might not be even necessary. So if I put, let's say, x equals t, where t is a parameter that is being used as auxiliary parameter, with the hope to make things simpler. So dx equals dt. Then from here, y equals minus t plus 2. And if I take the derivative, dy equals minus dt. So now the y, the x, and the dx and dy can be substituted in the formula to find out what would be the work done as the particle is moving from this point over here at the 2 point of the axis to the point C. So dW is going to be equal let's say 2x AX, sorry, we already said that x we substituted with t, so 2t, and there's a minus 2 obviously always outside, because this minus 2 comes from the fact that we have a particle which is 2 coulombs, so minus this thing, and then plus 4, and then we said y was minus t plus 2, and then this is ay, and this is multiplied by ay and dy, which is minus dt. Right here also, I forget to put times ax, and this is dx. right? So if we put all those things together, now we have somehow to make the manipulations with respect to t. So again, the same principles apply as before. In other words, ax as a unit vector times ax is going to give us equal to 1. Ay unit vector times ay, the dot product again is going to be equal to 1. So we're left with minus 2. And then we have here 2t dt. Now starting getting a little bit of mess, plus so obviously 4 minus 2 plus 2, and then minus dt. And we need somehow to integrate this again from the t takes the value, the same values as the x takes, so it takes the values from 2 to 0. So, interestingly enough, if we do that, and we do the calculations as before, as you can see over here, we're going to have minus 4t, and you integrate that. So it's going to give us this thing, minus and minus plus 8t minus 4. Same thing, this will give us this, and this will give us this. And the integration goes again from here, from the t from 2 to 0. And again, if we're diligent enough and do the calculations properly enough, we end up again with the same result as before. Yeah? In other words, I recommend you somehow to go through this process, go through the calculations, and you realize that this will give you the same result as before, 16 joules, and actually that was basically 24 minus 8. So this will end up again in 24, and this minus 8. So the net result is again this. So the conclusion you can actually derive from that is that the field is conservative. That's the conclusion. Now, the same conclusion can be derived with other ways. In other words, if someone asks you, given a field, to decide whether or not the field is conservative or not, you can go through a different avenue. So let me write the field again. So E equals 2x ax minus 4y ay. One way somehow to prove that this field is conservative, if we take the curl of the field and prove that the curl is equal to 0. Now we know that the curl of the field is going to be equal to I, j, k, partial with respect to x, partial with respect to y, partial with respect to z. And here ex, ey, and ez. Again, I'm using interchangeably I, j, and y, and k, and this can be ax, ay, and az. So basically we have here ax, ay, az, partial with respect to x, partial with respect to y, partial with respect to z, and ex is 2x, this is minus 4y, and this is 0. Now, the way we expand a matrix of this form is basically we take a pivot point, as they call it, let's say the ax or the ay and the az, so we choose one of the rows, and then we take the so-called minor determinant, which is basically we ignore whatever elements it is in the row that this element belongs to, so it belongs in this row and belongs in this column. And then the minor determinant is basically partial of 0 with respect to y minus partial of minus 4y with respect to z. And obviously both of them give us 0. Then the second thing is this point is the pivot point plus ay, and then partial of 2x with respect to z minus partial of 0 with respect to x, and this is also the whole thing is equal to 0. And likewise, the last element is this point, this pivot point, AZ, and then what is left inside is partial of minus 4y with respect to x minus partial of 2x with respect to y. So obviously, again, both terms of this is equal to 0. So the whole thing is equal to 0. So what is proven is this is indeed a conservative field. Something which actually was proven before analytically by finding the two different ways that you can go from one point to another point by following two different paths. And that's by definition what is a conservative field. A field that basically the work done by a charged particle along that field is equal to 0, right? If it goes in a closed path, or in other words, the work done by going in any path is going to be the same for a conservative field. Any questions? All right. Okay, let me repeat what we've done with this problem, and I will suggest you to pay particular attention on how to solve a problem similar to this because it might solve an exam. So what we have here, we have a field that's given by 2x ax minus 4y ay, and the question we're asking is, what is the work done by moving a charged particle of 2c, 2 coulombs in other words, from the point A in the diagram, which is the point with coordinates 2, 0, 0, to the point B in the diagram, which is the point with coordinates 0, 0, and 0. Subsequently, the same particle of 2 coulombs is moved from this point 0, 0, 0 to the point C, which is 0, 2, 0. And the question is how much work is done. The second part of the problem is now the same particle of 2 coulombs now is moving from the point A with coordinates 2, 0, 0 to the point C with coordinates 0, 2, 0. And again, this the same exact question. How much work is done by the particle moving from the point A to the point C? Now, if we find that those two works that's been done by this particle are equal, it means that it's an indication of a conservative field. Right, the way we find the work, again, we first take infinitesimal work by infinitesimal movement. So again, we have minus 2. Minus 2 refers to the charge of the particle, and again, 2x ax, and this is multiplied by the movement in the direction from the point A to the point B. So it's basically dx, and obviously it's in the x direction, so that's why we're using the infinitesimal, the unit vector ax, right? Hopefully by now, everybody knows that ax times ax, the unit vector is equal to 1. So the net result of this infinitesimal work that is being produced by the particle is minus 2, and then times 2x, in other words, minus 4x. Now we do the same exact thing moving from this particle here, from the same particle from the point 0, 0, 0 to the point 0, 2, 0, along the ay infinitesimal as a unit vector direction. Right, the formula for that is this one. So dy is minus 2 times 4y times ay. And again, this is multiplied by this infinitesimal movement along the ay direction. Same thing that I applied before. In other words, the unit vectors, the dot product is equal to 1. And we left again here with minus 4y, 8y I should say, times dy. Now, in order to find the total work done, we need somehow to integrate along those two paths and see what happens. And again, the x changes from 2 to 0, and the y in the BC direction changes from 0 to 2. So with this in mind, again, if we plug those things over here, Again, the x changes from 2 to 0, and then the y changes from 0 to 2. Just simply again some simple mathematical manipulations, and then we find the total work done in this movement. Now, the second part of the problem was what happens if the particle moves from the point 2, 0, 0. In other words, the particle now is here, it moves again here. So the final destination is exactly the same. But then the path that it follows is different. If somehow by find the solution to this problem gives us the same amount of work done, it's a very strong indicator that this is actually a conservative field, right? Now, in order somehow to do that, we say, okay, it can be done in a couple of different ways. The way that I thought was probably the easiest one is that if we take this line over here that connects the point A with the point C, and we want to express it as a line, we know it's a linear, so it has a slope, which is, we call it alpha, and also has a point that actually intersects the y coordinate, which you call it beta, right? So in order to find those alpha and beta, it's a very simple substitutions. Obviously, the line goes from the points A and C. So if we put the coordinates of point A, in other words, for x equals 2 and y equals 0, it should satisfy this equation over here, and that's what we do over here with those manipulations. And likewise, if we come to the point C, and we put x equals to 0 and y equals to 2 again, it satisfies the equation. So we have two equations with two unknowns, actually much more simpler than that. And then we can find that alpha equals to -1 and beta equals to 2. So the equation we're dealing with is y equals minus x plus 2. Now, if we want to parameterize this equation, because ultimately we want somehow to find what's the work done by moving the particle, the charged particle of 2 from the point A to the point C. It can be done possibly again a couple of different ways. There is a plethora of choices. Now, in what I thought was probably the easiest one is to choose x equals t, and if we take the derivative of x, it will give us also dx equals dt. Now, if x equals t, if we plug in this equation over here, if we substitute, then we find y equals minus t plus 2. Again, if we take the derivative here, we have dy equals minus dt. So we take all those preliminary findings and then we put it in the equation that tells us how much work is done, which is in essence the line integral of the components of the electric field along that particular line that is defined parametrically y equals minus x plus 2 or t equals t and y equals minus t plus 2, right? Plugging all those things over here and going through some sort of relatively simple mathematical manipulation, we end up again with the final result, which is if everything was done properly and not mistakes were made by not paying particular attention, we end up again finding the same exact solution as before. In other words, 16 joules. So this again is an indicator that our field is conservative. And that was the second thing. Now, another way to prove that the field is conservative, we can take the so-called curl. And the curl is given by this expression over here, right? Now, I think sporadically we express the curl with this matrix over here, where I put it both ways using ij and k as the unit vector, so ax, ay, and az as the unit vector, right? So in that particular case, in order somehow to expand this matrix, what we do is again, we keep each one of those as being so-called pivot points. And then if I, for instance, take point I as the pivot point, then I'm looking for the so-called minor determinant, which is basically whatever is left if I erase the elements of the row and the elements of the column where this I belongs to. And what is left is basically the minor determinant. Now, the sign that goes in front of this expression is that we take the minus 1, and then we put it m plus 1 as the exponent, where m is the row and n is the column in which this particular element belongs to. So if we do those things over here and then substitute the appropriate values for the elements of the electric field, we realize that all those, coefficients of the unit vectors, they all end up being equal to 0. So the whole thing is going to be equal to 0. So therefore, again, in a different way, our field is basically conservative field. Again, very, very briefly and quickly, repetition that this nabla, as they call it, this operator can be used in many different ways. You can apply it to a scalar field and it can give us a vector. And we call this vector the gradient. It can apply to a vector, and obviously the vector has various components, and then give us something, we call it the divergence of that particular vector field. And as we saw, also you can apply to, we're using, let's say, the cross product, and can give us what we saw over here. Right. I don't know what exactly is the exposure to vector calculus and what might be the limitations in terms of understanding those concepts, but I assume, I mean, if anything that somehow raises concern, I'll be more than happy to discuss it. Any questions on that? All right, let's do another problem. See if right. Now, well, before we move to this problem, is any questions of what we've done in the previous sessions? No. Right. Now, this particular problem, it's about finding the capacitance of a system that is relatively not necessarily complex, but not simple either. So we have a coaxial cable. We have an inner conductor that has, let's say, an electric density. Call it, I think, the statement of the problem, they call it sigma alpha. And this coaxial cable has an inner radius A and an outer radius B. And between the outer and the inner conductor is basically dielectric. So someone can make the claim that this constitutes a capacitor. So the first part of the problem is asking what is the electric field intensity and the electric field density of this system at any point inside, outside, and between the two dielectrics. And the second question is, what is the capacitance of this device? Right. Now, what can be done is, we start with expressions of the form like the divergence of D, the electric field density is equal to rho, where rho is the density of charge inside the system. This have also an integral form. And this expression over here basically constitutes a flux. So in that respect, if we want to find anything, usually we apply Gauss' law, which says that the surface integral of the electric field intensity is going to be equal with the enclosed charge within the system divided by the permittivity of the dielectric that exists in the system. Now, if we take d times ds, in this particular case of the coaxial cable, we need somehow to explore the cylindrical symmetry of the system. So we need somehow to choose a surface which is itself cylindrical. Now, in this particular surface, hopefully we know by now that the direction of the electric field lines is basically towards outside, emanating from the center of the coaxial cable towards outside, and basically the radius direction, in the radial direction. Yeah? So in that respect, as you can see over here, in that part of the surface, the vertical of the surfaces and the direction of the electric field are perpendicular to each other, so therefore the dot product is equal to 0. So the only contribution for this integral over here is along the so-called the curvature or the lateral surface of what we've chosen as being the control surface, right? So in that respect, again, both the things are, the unit vectors are the same. So the D can come outside. Now we have inside basically is the surface of the lateral surface. Now the lateral surface is 2 pi r, the circumference of the circle, and then times L, which is the length of this cylindrical surface that we took as control surface. So again, the first part of the Gauss law will give us D times 2 pi r times L. Now, in order somehow to find how much is the Q enclosed, the Q enclosed is the charge density which is inside this inner cylinder, right? And then likewise, we're going to have 2 pi. This time the radius A, which is the radius of the inner cylinder. And again, we have the length, which is L. So if we put all those things together, we find that the D is basically sigma and then A over R. And this is also in the direction of R, which is basically going outwards. Now, likewise, if we want somehow to find for the electrical field intensity, all we have to do basically is take this expression over here and then divide it by the permittivity of the medium that it belongs to. Again, it goes along this line. So hopefully this is clear. There's nothing there difficult to comprehend. Now, of course, the question now is, how do we find what is the capacitance? In order to find the capacitance, we know that the capacitance is basically Q over V. Now, the Q is relatively simple, it's basically the density, and then times the surface. And again, the surface, we call it A, and we'll see what A basically is 2 pi A times L. And this is divided by V. So let's see, whatever we found so far can actually prove to be useful in that respect. Now we have delta phi, which is basically V, and it's basically E dot product dl. Now E, we found it before, and it was sigma A over epsilon R and then we put it as r hat as being the unit vector in the radial direction, right? So this thing gives us 1 for the same exact reason as before. And obviously this goes from point A from point B, where A is the inner, let's say, radius, and B is the outer radius. So if we put all those things together, the sigma, the A can come outside, and the epsilon. And then if I have the integral from A to B of drr, hopefully we all recognize that this integral will give us the log. So the final result would be sigma A divided by the epsilon, and then the log of r, and takes the values from A to B. So in other words, sigma A over epsilon, and then log of B minus log of A. So finally, sigma alpha over epsilon, and then log of B over A, by making use of a particular formula for the logarithm, where basically the difference between the two logarithms is basically the logarithm of the ratio of the two entities, two quantities. And if we want, and again, this was V, this was the voltage difference, then I think from the statement of the problem it was given what is the voltage difference. So from here, we have this expression. And what we found that sigma, we can solve for sigma in other words, which is basically V, E, and then A, and then log of P of A. Now, this expression for sigma then can be actually substituted in the expression for the capacitance, sigma A over V. And you can see already certain things, basically, they will cancel. So we have V epsilon over A log, or write somewhere else, A log right. Well, I'll come at this point. So the capacitance in essence is V epsilon over A log of B over A. Yeah? And then we have A, the area, and the area is 2 pi A, that's the circumference of the inner circle, times the length, which is basically the length of the lateral surface of the curved surface of the cylinder. As you can see over here, the V's will cancel. With the V here, we have V also in the denominator, they cancel with each other. So whatever is left is basically the capacitance of this particular device. Okay. Let me go through and repeat the various steps. And this problem is also solved in the tutorial. So if you do have any difficulties understanding the various steps taken over there, we can always bring it for discussion the next time when we meet. The important thing again is that it's an interesting problem, very typical problem. We have a coaxial cable, and as you can see, coaxial cables have been used extensively in the technology outside. So it's a good practical problem. So what we have is we have a coaxial cable. We know that the charge density of the interior of the internal, let's say, part of the coaxial cable, and this is sigma A. Whenever we have a coaxial cable, the assumption is that the small cylinder, the internal, let's say, conductive material, it is positive charge and the outside is negative charge. We can also assume, because the surface of the outer cylinder is larger from the surface of the inner cylinder, that the density of the inner cylinder is actually bigger. Because again, the surface times the times the charge density will give us the entire charge, which is in both in the interior of the exterior cylinder, and we know that those charges are basically equal to each other, and obviously one is positive, the other is negative. Fine. Now we start with the expression for the divergence of the electric density, which is equal to rho. In other words, we start with this expression over here. This expression also can be written as in integral form. Those are one of the equations of Maxwell's, very famous acclaimed equations of Maxwell. Also, a lot of times we use interchangeably D and E, right? Magnetic field density, magnetic field intensity, that they basically relate to each other with the permittivity of the medium that they belong to, right? Now, doing so, now we need somehow to, for this particular case, we need to figure out what are those quantities. The first thing we do is we take the expression of the integral of d and the flux over the surface ds. Now, whenever we have a y, or whenever we have a cylindrical surface, and we want somehow to explore the symmetry, so we choose for the surface of interest that we want somehow to calculate this flux, a cylindrical surface that basically surrounds our cylinder, the small cylinder in this case, right? So everywhere there, because of symmetry, the d is constant, so you come outside, and what is left is the integral of ds, and ds is just integral of ds, but just simply the surface of that cylindrical quantity, right? Now we know that the circumference of a circle is 2 pi r, and the length here is L. So the whole thing is again 2 pi r times L. Now, this equation over here, the equation of Maxwell, also has a second, the right-hand side, which is basically the Q enclosed. Now, in order to find the Q enclosed, we have a surface density. So if you multiply the surface density by the surface area of the cylinder, it will give us the entire quantity of the charge which is there. And that's been signified by taking again sigma alpha times 2 pi A times L. A is again the diameter, or as to say, the radius of the inner circle, of the inner cylinder, and L is the lateral length. Right? So those things, put them together, will give us an expression of the electric field intensity with respect to the quantities such as the charge density, the permittivity, the internal radius, and the radius of the surface of interest, or the control surface. Now, I think this was the first question of the problem, how basically D and E can be expressed for this particular, let's say, arrangement of the coaxial cable at any point between the two or everywhere in the space. The second thing is, how do you find what is the capacity? The capacitance of this, because this constitutes obviously a capacitor. It has a charged cylinder in the interior, charge one. In the exterior, one is positive charge, the other is negative charge. And between them is a dielectric with a special permittivity, right? So basically we have C, we know that is equal to Q over V. Q is the charge, and then V is the vector differential. Now, the potential is given to us from the statement of the problem. And the Q enclosed is the density times the area. Yeah, that's the definition for density. It's a surface density. So if you multiply the density, the surface density by the area, this will give us the entire enclosed charge, right? So if we take this expression over here, that the differential in delta phi equals to V, and this is by relates, let's say, to the electric intensity by this expression, the line integral, and then we substitute E from whatever we found earlier, so we come up with this expression. DL can be the direction radial. So again, you have a unit vector r hat and then along dr. So again, do the same manipulations as in previous cases. We end up again with some coefficient over here which is constant, and then an integral which is dr over r. And hopefully we know from calculus that this is the integral will give us the logarithm of r, and the values, the limit of integration is from a and b. In other words, the radius from the inner and the outer cylinder. Again, and so we come up again more close form solution for whatever is the capacitance of this system. Right. I don't know if I want to say anything more in that respect. Is there any questions?
Recording stopped.
Right. If there are no any questions, then we can actually we can stop the meeting. If anything you want to discuss, I'll be more than happy to do so.